Have you ever wondered how scientists measure changes that are far too small to see with the naked eye? In this experiment, we'll heat a copper rod and track its tiny expansions with incredible precision using light, mirrors, and clever mechanics. Let's explore how physics turns microscopic motion into measurable data. In this video, we will measure the isobaric coefficient of linear expansion of a copper rod using a device called the Edelmann Dilatometer. The main part of this dilatometer is a container filled with oil in which a rod is immersed. We used a copper rod and olive oil. The rod in the oil is the rod whose isobaric coefficient of linear expansion, alpha, we want to determine. The principle is that we gradually increase the temperature, T, of the oil, wait until the temperature of the oil stabilizes with the temperature of the rod, and each time measure the corresponding elongation of the rod, delta L. The elongation of the rod shown in the diagram is greatly exaggerated for clarity. We increase the temperature of the oil using an electric current through a heating coil placed inside a glass tube. This tube with the coil is immersed in the oil on both sides of the copper rod. The temperature of the oil is measured using thermometers immersed in the oil. For small temperature increases, the length of the rod L at temperature T approximately follows this relation, where T is the temperature of the rod, L0 is the rod length at temperature T0, and alpha is the isobaric coefficient of linear expansion of the rod's material. Thus, alpha equals the ratio of the change in the rod's length, delta L, to the product of the initial length, L0, and the temperature change, delta T. Therefore, we must determine the proportionality constant between the change in rod length and the change in the rod's temperature. As the temperature increases, the rod expands because the atoms in the copper crystal lattice move faster and their maximum displacements during vibrations about their equilibrium positions become larger. The copper rod used in this video is 1 meter long at room temperature. At the end where the telescope is located, the rod rests against a fixed support, so when the temperature changes, it expands only to the left, toward the mirror. Near the mirror end, the rod presses on a lever that rotates the mirror. The thermal expansion of the rod, therefore, results in a slight rotation of the mirror. Just like in the previous video titled Measure Young's Modulus of a Guitar String, this slight rotation of the mirror corresponds to a change in the scale division, delta S, observed through the telescope. In the telescope, I see the mirror image of a ruler scale. The elongation of the rod and the oil due to small temperature changes is too small to be measured directly with sufficient accuracy. By rotating the mirror, this tiny elongation produces a much larger change in the observed scale division, S, in the telescope. And for the same reason as in the previous video about the guitar string, the relationship between the elongation of the rod and the change in the scale division observed through the telescope is linear. Again, as in my previous video about the guitar string, since the absolute elongation is measured indirectly using the change in the observed scale division in the telescope, we must calibrate this change to the actual change in the rod's length. In the Edelmann Dilatometer, this is done using a screw that shifts the rod when turned. One full clockwise turn of the screw, 360 degrees, corresponds to a displacement of the rod end by a constant A equals 0.65 millimeters. This shift has the same effect on the mirror as the rod's thermal expansion, because the rod expands in only one direction. Therefore, the displacement of the rod and its elongation can be considered equivalent quantities. If we determine the proportionality constant K between the rod displacement or elongation delta L and the change in the observed scale division delta S, and then determine the proportionality constant between the change in the observed scale division delta S and the change in the rod's temperature delta T, the product of these proportionality constants gives the proportionality constant between the rod elongation delta L and the temperature change delta T. By turning the screw 5 full turns, we obtain 6 points for the calibration graph of rod displacement, A multiplied by N, versus the corresponding change in the observed scale division, delta S, in the telescope. We fit a straight line to this graph, and the slope of this line provides an estimate of the constant k. When constructing the graph of the dependence of the change in the observed scale division on the change in the rod's temperature, it is sufficient to make 5 temperature increases, for example 4 degrees Celsius each time. The first temperature is room temperature, so we again obtain 6 data points. We fit a curve to this graph, and the slope of this curve provides an estimate of the constant x. The isobaric coefficient of linear expansion of the rod, alpha, is therefore equal to k multiplied by x and divided by L0. The linear proportionalities between the quantities are valid due to the small temperature increases of the rod. For very large temperature increases, these relationships would no longer remain linear, but that is not the case in our experiment. And that's how we can precisely determine the isobaric coefficient of linear expansion using optical measurement techniques. If you enjoyed this experiment and want to see more hands-on physics explained clearly, make sure to like the video and subscribe to the channel so you don't miss the next one.